In this video, I would like to demonstrate the workflow of the GPU usage characterization that we've undertaken as part of a SPICE video streaming project. And this characterization is done with the help of the Streaming Stat toolbox. So the context is that we have a virtual machine running with QEMU hypervisor, and its desktop is exposed with SPICE. And this desktop is exposed with a video stream encoded with a vGPU. So let me highlight this. If I connect to the virtual machine and list its devices, we see that the virtual machine has an Intel GPU that is exposed by QEMU. So I can start a WebGL example. So it takes a few seconds to load and it goes full screen. So this is an example of the use cases we use to characterize the GPU usage. I stop it. And we can switch to the recording infrastructure. So here we have 3 agents connected to the streaming agent, the client, and QEMU. This agent will collect local information about SPICE and about the system, like the memory usage, CPU, and GPU usage. And the fourth component is the performance collector that will gather all the performance indicator and either save them to disk or show them live. So first I will show the live infrastructure. So we have a control center where we can specify the video encoder and different settings. So if I clear everything, I apply the framerate 30 with the default bitrate, and I can switch to the different tabs, and we see the performance usage in real time. Same for CPU, frame size, etc. And if I change the setting, I put a low frame rate, I activate it, and we see that when the setting is activated, the GPU consumption drops from around 50 to around 15. Same for the server, it's more the same device, only that it's split. On the frame size, we see that the keyframes are more sparse than before. So this step was the live step to have a quick understanding how things react. But to characterize the GPU, we want something more automatic. So let's switch to the benchmarking mode. So the idea of the benchmarking mode is to run the different workload on the VM, different things on the screen, and apply different sets of parameters and understand how one setting affects the resource usage and another setting will change it. So here we see that we will record for 40 seconds In the current configuration, we will run these 5 experiments that will study the impact of the FPS, the resolution, the bitrate, the keyframe period, and the content of the display. So if we look in details at these different experiments, it's always the Intel hardware encoding with VP8 codec that will be used. And for the FPS study, we will set all of these different frame rate values for 3 different bit rate, 1 keyframe period, and to have a good understanding of the different situation, we will use these 2 displays, one WebGL, one static image, and 2 resolutions. If we look at the resolution study, in this one we'll have only 2 frame rates, but many different resolutions, all in the 16:9 ratio. And same for the bitrate, same for the display study and keyframe period. So I can run the benchmark in dry mode to have a look at what it will do. So all the combination of this setting led to a total of around 300 experiments, and with 40 seconds per experiment, it would have taken something around 4 hours. And for each experiment, the script will apply the different settings. Here, the settings for the encoder, the setting for the script. It will clear the recording, ask the different agents to share information such as the resolution, the encoding, and also we share the JStreamer pipeline to have a very precise understanding of the parameters of the benchmark. And then, when everything is applied, we wait 40 seconds, save the result, and go to the next experiment. Now, once the experiments have been recorded, we can launch the viewer mode of the tool. And we've got all of these experiments loaded in memory, and we can have a look at the matrix visualizer interface. So let's start with the FPS study, and we look at the guest render GPU. So here we see all the results that have been executed. There is only 1 keyframe period, so we can already set this. Currently it's sorted by bitrate and experiment. If we sort it first by display, we have 2 different resolutions. So we see that for the static image, the GPU usage is between 11 and 30, and for the WebGL, it's much higher, between 50 and 70. We can also focus on the static image, and for our 2 resolutions, we see that, of course, the bigger resolution, the higher the GPU usage, and same for the lower. Now, let's study the relationship between the frame rate and the GPU usage. So we select regression between the GPU and the guest with the frame rate. And we see that for all our plot, if we put them in the right position, we see clear tendency, linear tendency for the relation between the frame rate and GPU usage. And we can see that for these two resolutions, the bitrate has barely no effect. So currently we have all of these curves. We can select one bitrate and narrow the number of results to two equations, one for each resolution. And we can do the same with the resolution. So we take the resolution study, have a look at the regression, GPU and resolution, and the guest. So again, we see that for the still image, the bitrate has almost no effect. In fact, it's the same also for the keyframe period. So we can set it. And the frame rate and the display have a more significant impact. So for the next step, we want to combine the frame rate and the resolution to understand the overall impact on the GPU render engine. So let's start with the WebGL display, and I'll do the same for the still image. So WebGL, and now we've got two equations, one for each frame rate. We do the same here, two equations, and now we can take this equation and put them in a solver. So I take it, I give it in my custom solver. I need to remove this and that. So what this equation says is that for a resolution of 2 megapixels, the GPU render usage will be computed by multiplying the frame rate by 0.53 and adding 45. And same here. And if we take these two equations, we give it to the solver. Now we've got 4 equations defining the relationship between the frame rate, the resolution, and the GPU render. So I can kill this one, and I can run the solver. So the solver will combine these 4 equations in many equations, because they are approximative, they are not exact modelization, and we see them on a 3D plot. That's the plans defining the relationship between the parameters. I can hide some of them. 27 and 46. So we see that the plans define more or less the same solution. And if I select only the initial equation, we see that there is a plan that is shown, but if we zoom at the intersection, we see that it's not a true plan. That's why we have many different solutions that use more or less 2 equations each time. And we could get exactly the same behavior for the still image. So now we can inject back this coefficient into the streaming stat toolbox. So we had equation 15 highlighted. So let's switch and take this plot model for the GPU. So we were using the WebGL modelization, the WebGL display. So I need to fill FR, AF, AR. So AR is the one multiplying R. So this. AF is the one multiplying F and R. And last one is here. So I save this, I comment this one, and we use my old computation for the image lady. And we run the viewer again, and we go back here. Now we want all the experiments, everything, this I don't need, every plot model of the GPU render. It takes a little while to load, but there we are. So yeah, we should have the parameters we were using before. So what we see on this graph is the plan we've defined, and the dots are all the experiments that were executed, and the color tells the distance between the plan, the computed solution, and the measured solution. And we see that in this experiment we get a maximum of 10% of error, between -5 and 10. And we can also add the still image. Takes again a little while to load, but there it is. So again we've got between 5 and 10% of error, and now we've got 2 plans showing the relationship between the resolution, the display, and the frame rate. And we did something similar for the CPU. Here it is. So the error is between -6 and 3. And we've got, again, 2 plans for both display usage. Thanks for watching. Bye bye.